Shall we get it going?
Yeah, up to you.
Yeah, let's do
You're
it.
the boss.
All right, everybody. For those of you trickling in, why don't we start moseying towards seats so that we can start our next session? Okay, welcome back, everybody, to our next keynote speaker. So my name is Angela Radulescu. I'm faculty at the Mount Sinai Center for Computational Psychiatry, and it is my pleasure to introduce our next speaker, Dr. Bean Kim. Dr. Kim received her PhD from MIT in 2015 and is a senior staff research scientist at Google DeepMind. She is a leading expert in explainable AI and has pioneered approaches to study interpretability of AI systems. In fact, the first line of her thesis, all the way back in 2015, reads, I envision a system that enables successful collaborations between humans and machine learning models by harnessing the relative strength to accomplish what neither can do alone. She has since worked on developing and critically examining interpretability methods with the goal of keeping us humans in the loop and ensuring the technologies that are shaping our research and lives are in line with our values. She has given keynotes at ICLR, ECML, and the G20 Summit, has received the UNESCO NetExplo Award, and was featured in Brian Christian's book, The Alignment Problem, and has been elected as the ICLR General Chair in 2024. So without further ado, please welcome Dr. Bean Kim.
Thank you. Thanks for that generous introduction. Thanks, organizers, for having me. I did my PhD here at MIT, and this auditorium I've only been on as an audience for a choir performance and whatnot, and it's first time being on here. It's special to me. And now I realize why previous speakers couldn't hear the questions, because there's like interesting echo going on. So I suspect that might happen again. So I am not a neuroscientist. I'm not a cognitive scientist, though I'm passionate about studying complex things like you do, complex things, humans and machines. And I've been fortunate to be in this field of AI at what seems like at the right time. We seem to be able to make complex machines that are as capable as humans, sometimes better, sometimes. And I've been studying these machines and looking at how they work, sometimes at the levels of bolts and nuts, sometimes at their behavioral level. A lot is yet to be understood, but it's been such a fascinating journey. I am excited to share some of it with you today. But I'll be honest, I have an agenda today. And my agenda is to get some help from you. You who knows really well about how humans work. Because this moment is crucial in humanity. Machines are progressing so fast and impacting everywhere in our lives. And we have to decide and figure out how are we going to have these machines living with us? What are our relationships? And perhaps most importantly, how we're going to make these machines work for us and not the other way around. So to answer these questions, we have to know both how machines work, but also how humans work, because humans are the part of the equation. And knowing how humans work is important in making machines that are useful for us, because you gotta know the users. And also, studying machines will have to use the insights from how we study humans. In fact, the most complex thing that humanity has studied for the longest time are humans. So it's only natural. So this talk is about hopefully one of many ways where we can make machines work for us and not the other way around. And in particular, we're going to focus on how we can advance human knowledge by using these machines. But my talk would be only successful if I inspire you to think about your own ways from your expertise how to make machines that could work for us and not the other way around. So let's start by thinking about us. Here's a circle that represents things we know. You can think about this as vocabularies or concepts, and concepts that those vocabularies can explain, medical knowledge, etc. And these knowledge makes us capable of things, advancing technology, cure diseases, etc. So these circles not only include vocabularies and concepts and knowledge, but also capabilities. Now suppose we can create machines that only can know and do a subset of what we can do. But maybe they do it faster, more accurately, and they don't get bored of doing it. And we, in fact, have many machines like this around us: ATM, autopilot for trains and airplanes. So I suppose we can only focus on machines like this. And some might argue, and has argued, that this is the safest approach. But of course, the truth is this: the machines we create are weird. But we can create them, but we don't understand them. We don't know what kind of knowledge they have, vocabularies and concepts. Because of that, we have a poor understanding of what they are capable of. Now that sounds a little like sci-fi. It kind of is. Even before AI boom, while humans have created machines that are better than humans, like in chess, they were rule-based. So that means that we can look into it and figure out how it does what it does. But now AlphaZero, a chess machine that DeepMind created, this is a chess machine that surpasses any human in Elo rating, a superhuman chess machine, is neural network based. So we don't know how it does what it does. And we'll get back to this story of AlphaZero later in this talk. So this naturally raises the question, if we don't know what machines are capable of, we better be very careful using them. Specifically, we have to think about how to create these machines that contribute to us. At the end of the day, we're creating and spending time and money and energy to train these machines so that they can be useful for us. And we definitely don't want to live through one of these doomsday sci-fi endings. So how do we do this? Well, let's first think about how humans bridge the gap when they have fundamentally different values, concepts, and capabilities. Maybe that can give us some insights. Think about two people from different cultures, and we're trying to align their values to improve some mutual understanding of a situation. I'm Korean. Let's say I'm person B, and I want to explain some of the Korean values like 정 to person A. Who here knows what 정 is? Some of them. Okay, you can point me if I'm butchering this concept, because it's so complex, it's so beautiful. So 정 is something between love and like. It's more than liking, but less than love. It's never a romantic one. And it has to grow in you. It doesn't just happen. There's no 정 at first sight. So this concept stems from foundational principles of Korean culture. So in order for you to really understand what 정 is, I have to tell you a lot about Korea and our culture. In other words, you have to expand what you know to understand this concept. And I'm sure those who are bilingual in the audience have something similar in your language. Words that cannot quite perfectly translate between languages, even with a lot of context. So this sort of communication becomes critical, especially when it comes to communicating values, from resolving conflict in multicultural families to sometimes the world peace. The alignment problem is the word that we use to describe the same thing between humans and machines. Who here heard about the alignment problem? All right, quite a bit, great. Communicating values, which then drives their behaviors. So to build machines that are helpful from ground up, aligning values is important and is a more efficient way to achieve the desired behavior. And similar thing happens in the alignment problem, except the gap between humans and machines are now bigger, because we don't even share basic things like food and survival. In fact, there's likely this potentially huge space of machine knowledge and capabilities that humans are yet to understand. From this diagram, it's called the set M minus H. And this is the set that where unexpected behavior of machines that could be potentially dangerous and we weren't prepared for may come from. But also, this is the space where that beautiful move 37 AlphaGo made came from. Who here know the move 37? Oh, who watched the AlphaGo game? Great, this is more than my usual, because this is great. It shows the generation in the audience. So this move 37 is that AlphaGo played against Isedo in 2016. I watched every single match. It was a big deal in Korea and worldwide too. And this, when the AlphaGo made this move, I remember a commentator who is 9 dan, the highest dan you can get in Go, was really chatty before then, and like he suddenly paused. And he was like, huh, this is interesting, and went quiet for a while. And I knew, I got goosebumps, I still do. Like I knew something very interesting has just happened. And this move 37 is the move that Go players still talk about. We have some understanding of this particular board position, why AlphaGo made that move that turned the game around to its favor. But we don't yet understand the underlying principle of this strategy so that we can apply to different board position. We don't know, but we all know, we know that it's beautiful. So M minus H is also where this knowledge, like beautiful knowledge like move 37 came from. And that is the space that we're interested in. Now, alignment problem is easier if M is H, because once you identify what you want to align, let's say values, then you can focus on the technical problem to figure out how to align. Now, I'm not saying that figuring out what to align and figuring out the technical problem is easy. It's very hard, active area of research, but at least you can start to define something. But the truth is that that's not the case. There might be values that we have, humans have, but machines are incapable of understand, represent, etc., because it lives outside of things that it can represent. Also, there might be values and concepts that is beneficial for us, like knowledge, for example, that lives outside of a human space but only lives inside a machine space, M minus H, and we won't be able to align that value either. So what do? We expand what we know, and that will enable us to create machines that can better communicate with us. So interpretability is a tool to enable this communication, and I argue that expanding what we know should be the main goal of interpretability. And to be absolutely honest, I don't know how else we're going to achieve this. And maybe to some extent, maybe we can achieve some alignment without thinking about expanding ourselves, but I wouldn't be comfortable having these machines around if that's the only thing that we're going to focus on. So I'm not saying also that we should expand so much that machines' knowledge should be part of human knowledge. That will never happen. We just have to expand enough to sufficiently communicate important values that matter, like we do with people from different cultures. So a better way to do interpretability is to teach humans new concepts to understand and communicate with machines better. And by doing so, we're not only in better position to understand unexpected risks, but also we can even benefit from them by pushing the frontier of human knowledge. So we can not only survive, but thrive. We'll get back to this later. You can also go beyond interpretability, beyond knowledge transfer, by thinking about what each other is thinking about. This happens between human learning. A nice framework to think about this is inferential social learning, pioneered by Conero 2021. And this idea was originally proposed as an account of how humans learn from others and help others learn. The idea of building mutual mental state can serve as a useful guide for generating new research ideas beyond interpretability to make human-machine interaction more informative, productive, and beneficial for humans. And these are some directions that I haven't seen a lot of work on. And if you're a PhD student and thinking about topics, this is a great direction to put more thinking on. But this talk, I'm going to focus on interpretability. So I argue that expanding what we know and making this blue blob bigger is a good idea. But you might think, well, that seems really hard. Can we just do a simple thing first? Can we just focus on what we and machine both know, M cap H? Can we just get something done by doing that way? So let's talk about that. What happens if we pretend M is H? We can talk about that because that's how we used to think about interpretability. We wanted to shoehorn everything into M cap H and pretend that take something that machines know well better than humans and hope that we can understand something from it. Lots of methods were developed, feature attribution, feature visualization. I developed many of those methods myself. Unfortunately, after many years, we realized that they don't really work as expected. And this is not to say that they don't work. They just don't work in a way that we think. In many of my work last years, often accidentally discovering many surprising ways these methods don't work. Many of them, we still don't understand why. And bring this out to the light is important because having the feeling of and comfort of that you know something is worse if it's incorrect than knowing that you don't know anything. So let's gather some evidence to answer this question, is M really different from H? And that we can even solve some problems by focusing on M cap H. We'll do this from two angles. First, fundamental perspective, by which I mean asking questions of are there fundamental principles that differ between humans and machines. And to answer this question, we put machines in front of tests that we usually give it to humans and see how it does it. Second is application perspective, by which I mean the evidence in the application of deep learning that highlighted the difference between M and H, often or sometimes to a shocking degree. First, fundamentals. The first question was about perceptual differences. Machines seem to classify objects really well. One may argue that the first breakthrough in deep learning happened in 2012 when AlexNet was announced with using convolution neural network that broke and beat every single approach that came prior to it. And since then, more deep learning approaches proved to be very effective in visual classification. In fact, superhuman performance in ImageNet classes of those 1,000 classes, dogs and cats and many other things. So a natural question in our mind was, does the basic perceptual phenomenon happen in neural network too? Gestalt effect is, I'm sure many of you are familiar with this here, is a very strong visual tendency for humans. A subset of Gestalt effect is shown here, the law of continuity, where we see these dots as a continuous trajectory of something. And in this particular work, we test the law of closure, our tendency to complete an incomplete shape in order to rationalize the whole. Like, we view these three brackets as triangle. The Gestalt effect is so strong in humans that even if you know the fact that these are not a full triangle, you can't unsee it. Try it. Is it triangle? It's still triangle. You can't unsee it. So we did what's the simplest possible to answer this question. We take a neural network, and we gathered activations. These are internal embeddings of these triangles, and we use them as a proxy for how the neural network is thinking, similar to it's done many talks that happened before the contributed talks. By the way, all of them are very, very interesting. Then we calculate how similar the aligned triangles are, aligned and complete triangles are in their activation space using cosine similarity. This is simply comparing whether they're similar or different. Then we define closure measure, which is the similarity between the aligned, the Gestalt provoking picture, and the complete actual triangle, minus similarity between disorder, the non-Gestalt provoking picture, and the triangle. And what that does is that if there is a closure effect, it's likely that neural network views aligned, the Gestalt invoking picture, to be more similar to an actual triangle than it views the disordered to a triangle. We control for many confounding factors like background color, position, and angles of these brackets, etc. Although this is not the complete set of possible confoundings, it does address some of the superficial confoundings like pixel overlap. So here's the result. Y-axis shows the closure measure, the one I explained just now, and X is the edge length of these brackets, as it's done commonly in human experiments. What we learn is that if we train the network normally, which means if I give a cat picture, I said it's a cat, give a dog picture, it's a dog, then it does seem to have a very similar pattern to how humans respond as these edge lengths increase. But if we give them a lot of pictures but random labels, we gave it a cat and sometimes said it's a dog, and the dog to a cat and tree. In other words, it doesn't know how to generalize. Then we saw a significantly less closure measure happening. And furthermore, if we shuffle the pixels, so it's a cat picture, we shuffle them around, no longer looks like a cat at all, but it's a correct label, then we don't see any Gestalt, very, very small Gestalt effect. So this tells us that Gestalt effect only happens when models can generalize. In other words, when they learn meaningfully, but not just when it sees many examples. So in other words, it may or may not be inherent perceptual tendency. It's rather a result of a pattern-learned behavior. Now, I'll add some speculation here, because apples-to-apple comparison is very difficult here. We can't do a time-limited exposure to neural network like we do with humans, because there's no mechanism to do that. But it hints that maybe the baby neural network, the one that was just born and without no generalization ability, don't have the Gestalt effect, although I suspect that human babies may have some of these, even though they don't know all the 1,000 classes of ImageNet very well. So second fundamental perspective of difference between machine and humans is by simply asking if generative models learn to count like children. There are many interesting theories quantitatively and qualitatively about how human children learn. Apparently, they learn from 1 to 4 slowly, but then learn all the rest pretty quickly via induction. And it's context dependent. If you ask a kid to give a treat, one treat each for each dog, they do pretty well. But if you tell them, give this freeze-dried pea to each your toy trains, it's less good. So context matters. 3-year-old who can count to 10 may understand 8 is not 4, 8 is greater than 2, but they may not know that A is greater than 4. So there's some nonlinear learning going on here too. So we studied how well generated models can count by asking it to generate images given different number of objects. And inspired by all this developmental psychology work, we asked the model to generate images of not only common objects, but like apples, but also uncommon objects like hairy oranges. And to see how the context-dependent these models are. We also asked different media. It's likely that 5-year-olds understand what 9 apples are, but it's unlikely that they can produce a graffiti of 9 apples. So we were curious if the media makes any difference in generative models too. Here are some of our findings. First of all, the scale of model matters. As you know, the scaling, making models bigger in terms of parameter, unlocks capabilities, and counting seems to be no exception. We saw a drastic increase in counting ability at 3 billion model scale. But they don't learn like children do. It learns 1 to 4 reasonably well as model size increases, but induction doesn't really seem to happen. And they don't learn 8 and the rest of the numbers very quickly at all. Surprisingly, however, of course not surprisingly, models can produce different media pretty well, despite that it doesn't know how to count. In hindsight, it makes sense because there are probably a lot more of these media in their training data set than human children sees these different media of pictures of apples. But seeing this phenomenon in data was pretty interesting. However, if you're like me in the audience, you're looking at this graph thinking, what is that peak, that weird thing in the graph? So one unexpected behavior that we observed was that all 3 models have this mysterious peak at performance in counting 9. Why 9? Do you want to think about any hypothesis? They don't know 5, 6, 7, 8, but it just knows 9 pretty well. sorry to tell you that I don't have a true validation of this. We have speculations. And here's our hypothesis. This can be only qualitatively validated, but when we ask it to produce 9 things, it loves to produce 3x3 grids. So we suspect that maybe training data had a lot of these 3x3 grids for some reason, maybe textbooks, I don't know. We're unfortunately unable to validate this hypothesis because this was curiously driven project, and retraining the big model without the 3x3 would have been costly. Another interesting thing is that the context did matter. Asking to produce uncommon object did cause the model to be less accurate. So in that way, it shares some similarity with children, but overall, it's fair that models don't look like it's learning how to count exactly the way that human children do. So far, we looked at how machines differ in fundamental perspective, focusing on perception and counting. A second perspective on how M and H are different in application perspectives. So after 2012, many folks in machine learning were interested in how deep learning models classify images, sometimes at superhuman level. So many methods were developed, and I was one of the many people who developed many of these methods, and which now we categorize as saliency maps. And I realized that lots of talks actually use this some sort of this heat map styled things. So for those who are familiar with saliency map and feature attribution, yeah, so most of you, perhaps, I will go very quickly. It's just different frame of thinking about feature attribution. What is this? It's a family of technique that for each feature, like pixel in this case, has a number, and that number represents how important this pixel is. In other words, and this what important means, it differs depending on the method, but usually it measures some shape of the function, where this function is the probability of bird, let's say. So if I take this pixel and wiggle it around, does the probability of bird go up or down or flat? So it's looking at the shape of the function. And this was an appealing solution. The saliency map of bird picture showed a bird-like thing. And it seemed plausible that these pixels are, in fact, why this picture was classified as a bird. We didn't have the ground truth, though, because we still don't know why these pictures are classified as birds. But humans are humans. We like to see things that supports our belief. But let's think about this a little more. The reason that we wanted to see make these saliency maps or feature attribution is to explain models' prediction. So in other words, when we look at these saliency map, we are internalizing that, this map, whatever that I'm looking at, the explanation, is influenced by model's prediction. That's pretty naive and obvious conclusion that we will reach. It turns out that it's not the case. In this 2018 work, where we showed that if you have a trained network that meaningfully classifies cats and dogs and other 1,000 images, the saliency map of that is qualitatively and quantitatively indistinguishable to another network that predicts random. This is untrained network that randomly says cats and dogs. In fact, it's so indistinguishable that I flipped these two and you probably didn't even notice. Can you tell? Pretty much the same. You can't tell. And this work results in 2018 really bothered us. So we did empirical work to put these maps in front of the users and give them some tasks to see maybe these maps are useful for some tasks. But we realized that it doesn't really help either. But we always wanted to have some theoretical results to really understand what's going on. And that's what we did last year. So our expectation is close to the sentence from one of these work that says these methods can be used for accounting the contributions of each feature. In other words, if the tool says this pixel has 0 attribution, then we infer that this pixel is unused by this function, function f near x, and f is insensitive to perturbations of this feature. If I wiggle this feature around, nothing's going to change. And in fact, this is how it's been used. This is a quote from one of the papers published in Nature, where they used one of these methods to decide who is eligible for medical trial. So it's pretty serious business. Now, in this work, we theoretically prove that just because this method tells you it's a 0, does not mean that you can conclude that model doesn't care about this feature. So none of this, what seems pretty obvious inference in human minds, were not correct. Now, it's not to say that these don't work. In many cases, they do add values, and we have seen literature of some of those examples. But these work point out that we have to use these methods with great caution. But unfortunately, humans are not great at caution. When they see something that they like, the caution goes out the window. Most of these methods were developed for many years, like close to 10, before we realized any of these. And these methods are developed with good intentions. I developed some of these. I had good intentions. We just hoped that pixel-based explanations would reveal some insights, but humans don't think in pixels. Who here think in pixels? We don't. Machines do, though. So ignoring these fundamental differences wasted our time at best and gave us comfort of understanding machines when we really don't. So now, assuming this M minus H doesn't exist isn't just not a good idea in saliency map and ImageNet classes, but also in large language models. So in this more recent work, also started by thinking about, let's locate some knowledge in these LLMs, and quickly went down the rabbit hole and discovered that surprising discovery that localization has nothing to do with editing success. What does that mean? Localization is a word that we use to refer locating where a knowledge is. Let's say I want to locate where the cat lives in this neural network. It lives somewhere in the last layer in these 2 neurons. And what that means is that when I say, what a cute blank, then the model is going to continue my sentence by saying, what a cute cat. Editing means that you go into those neurons and mess it up. When you mess it up, you erase these cat neurons. Then when I say, what a cute blank, it's going to say, what a cute something else. And that makes sense. You locate the knowledge, in our minds. You locate the knowledge, you mess it up, and it goes away. That's sort of really obvious inference. It turns out that that's really not the case in this neural network. There's no relationship between the location of knowledge and editing that versus editing something else. And measuring the editing success. And if we find, in fact, the choice of the layer was explaining most of the variance of the 94% compared to tracing effect. Tracing effect is the fancy words for localization. And this is using a framework called ROAM, which is I human, look at it, and it's legit. It's a framework that should work. It makes sense. It's principled. It's nice. But somehow, that localization method still does not correlate with editing success. So we thought, OK, maybe editing means a lot of different things. We can edit in different ways. So maybe there is a type of editing that does correlate with this localization. So we tried every single possible that we can think of, definitions of editing. You can inject error, you can reverse the editing, you could erase the flag, you can amplify the flag, everything. And none of them was related to localization. We still don't know why this is the case. There are some theories of why this might be the case, correlations of directions, but I honestly, after this project, had many more questions than I began the project. So this is, why is this case? I think it's just not how machines think, and we still don't know what it thinks about this case. So even something similarly benign logic like relationship between localization and editing might be from M-H. So hopefully, I have convinced you now somewhat that ignoring M-H is a bad idea. We have to think about M-H. So then your question might be, well, how do we do this? This sounds really hard. And here's a few reasons why you should be skeptical. How do we know machine is beyond human? It's beyond us, and we're the ones who are trying to tell. So how do we know? Who should we teach? If we were to teach this M-H knowledge, we have to identify who are at the frontier of human knowledge. But if you get our 10 great world's best doctors in one room and give a case, they will all likely disagree with the very reasonable backings for their claims. So it's very hard to figure out who are the experts, who are really at the frontier of human knowledge. How do we verify that we learn something new? It's something new. I don't know what that is. So how do you even go and validate this, even if you were successful? Chess is a great playground, a mini version of this, to show that this is possible. In chess, there is a clear signs of who won and who lost. And there's an elo rating that can rank every single human as well as machines. We have many tournaments every other week, if not every week, to figure out who's the best at playing chess. It changes every so often. So we know that who are the frontier of human knowledge in chess. We can also validate they have learned something new by quizzing these grandmasters if the new knowledge made an impact on their moves in unseen positions. And we'll get back to this. And luckily, we also have a AlphaZero, which is a superhuman chess network, based on neural network that beats Stockfish engine, which is the best chess playing machine out there, only within 4 hours of training via self-play. So it plays against itself, and it gets better than Stockfish within 4 hours. So that's a nice tool to have. The question is, okay, this setup makes sense. Is this even possible? First, you might wonder, well, this chess machine was trained by playing against itself. That means that it has never seen how humans play chess. So you might ask, does this have any MCAP-H? Is there any overlapping concepts between human and this machine? Previous work, we showed that, yes, there is some human concepts do exist in AlphaZero. In this work that I will present in this talk is going to be about teaching this M-H knowledge to amazing 4 grandmasters that we worked with us over the years. Vlad, the world's longest chess champion. Gukesh, who just won the tournament to challenge the world chess champion title in this winter. Hoi Fan and MVL, active and amazing grandmasters that we were very fortunate to work with. I also want to highlight Lisa Hutt, who was lead author of this paper. She used to be in her previous life a professional chess player and champion herself, but now decided to machine learning and do a PhD at Oxford. And without something like this arrangement, like stars align, this kind of project wouldn't have happened. And even then, it took us a few years to make this happen. So without going too much detail into the method, I'll show you a little bit of flavor of this, our method to learn those superhuman concepts. And the reason that I want to share a little bit snippet of this is that while this work, we really focused on getting superhuman concepts from chess machine, this particular chess machine, I think some of the ideas can be extended to many other domains because they're quite simple framework. We have some ingredients, data sets, and 2 AlphaZero models for the reasons that will be obvious soon. And we put those into convex optimization, constrained convex optimization framework using the representations of this AlphaZero. Then we filter concepts, a lot. And we'll talk a little more about this. And the reason that we filtered a lot of concepts is because we only had 1 shot with these grandmasters. We send it over quizzes, cross our fingers, and that's it. So we had to be very, very picky. And we couldn't really, we don't know, they're grandmasters. So there's a lot of things I'm sure that they know that we can't interpret. So there's a lot of nervousness when we had to send it off. So we have to be very careful, and we need a very small set of under very strict guideline threshold for quality. And we evaluate with methods, but also human, the grandmasters. First of all, you might be wondering, what is concept? Here's a casual definition of a concept: a unit of knowledge that contains information useful for a task. And it might have many properties, some of which are minimality, that it has cut out some fat, it's got concise information in there, and it's transferable, that it can be taught. There's some generalizability in it. In chess setting, we assume a concept gives rise to a plan that player implements, which is a deliberate sequence of actions. You can operationalize this definition in many different ways. We do it in the following way. We represent the concept as a sparse vector in an embedding space of this network. And we show that we can transfer this knowledge to another AI at the filtering step and eventually to humans. AlphaZero has two components, in case you're not familiar with it. It has policy value network. This is just like regular neural network that you all know. Most of you are familiar with. And then there's MCTS. It's Monte Carlo tree search. And to make the final decision, it consults with both of them. MCTS is like a tree that you can think about planning moves. So here you see let's say I am in, I can't point, let's say I'm in that green circle and t equals 0, and you could make any of these circles as a next move. Let's say you chose another green circle down there, and every move that you chose, there are moves that you didn't choose, which are marked as the red circles. So what do we do to learn these concepts in this vector is give me the sparse vector such that this vector, oh, I have laser. This vector, no, I don't have a laser. This vector, the concept within this vector is more strongly present in the chosen path, the green ones, than unchosen path, the red ones. And because in every single step, you have path that you didn't choose. So we can get lots and lots of constraints like that. And if there is a concept that's consistent across those paths, then we would be able to learn some meaningful vector here, incorporated in VCL. Then we filter concepts. We spend a lot of time figuring out what's the right way to filter concepts. First, we filter based on teachability. Is this concept teachable? We do this by ensuring these concepts can be taught to another AI agent, because again, we don't have that many time with grandmasters, and also we actually couldn't find chess players that good enough to even teach some of the concepts that we learned, even at the level like Lisa, who is the first author. She understands everything, but she was best in chess, and everybody else, from what I heard, in DeepMind, except Demis, maybe they haven't had a match yet. So we had to use the AI agent. And in other words, can we teach this student agent apply the concept to unseen positions? And we do this in following a very simple way. We get some examples, the prototypes, that these concepts arise. And then we teach student agent by minimizing the KL divergence between the policies of teacher and the student. Then we test the student AI agent with unseen data. So if this concept is something general enough that arises in many different board positions, and the student is able to acquire this concept, then you will see teachability. It will pass, the concept will pass the teachability filtering. And after this, we filter 96% of concepts. There's lots of thresholds we can set, but we just decide to be very strict. Novelty. We enforce novelty in two different ways. One, by construction. So we have two AlphaZero models that at the end of a training, let's say at T epoch, and we also have an AlphaZero network that is 100,000 epochs before that, let's say T minus K. We only look at positions that the two AlphaZero disagrees. Now, both of these AlphaZero networks are already superhuman in ILO rating. But we are just doing this to really ensure that this concept was arised between that T minus K epoch and the final T. We also do this by defining novelty score. This is best explained by thinking about this, bringing the circles back in. Now, we can learn, sort of pretend that we learn human basis vectors. We don't understand what these vectors do, but we can have unit vectors by decomposing a bunch of human games, the ZLH. And we can do the same thing with AlphaZero games. We have a lot of AlphaZero, how AlphaZero played its games. And these are sort of like, you can think about it as a vocabulary or unit vectors, and together they can represent concepts in that space, the human games or AlphaZero. So it's like a language. And we say a concept is novel if it's better reconstructed using AlphaZero's basis vectors, AlphaZero's language, than using humans' language. Because you're novel, then it's likely that you are more fluent in AlphaZero's language than human language. Finally, we quiz these grandmasters. The way we do it is we have prototypes from some set of concepts, and we split that into training and testing. We send the training board positions to the grandmasters, and they ask them to make a move. And then second phase, we teach them by simply showing what AlphaZero would have done on those board positions. And then third, we quiz them. We give them the test board positions that they've never seen it before, and we ask them to make a move. And as you see, all players, some of them significantly improved their alignment with concepts, how AlphaZero would have played on those superhuman concepts. And note that we're avoiding any potential failure of explanation methods by not using them at all. We simply show grandmasters what AlphaZero would have done. And by doing so, we're heavily relying on our grandmasters' ability to connect the dots and filling in the gap in human knowledge and relying on them to expand their vocabulary. So to give you some context of these numbers, despite very small sample size, these grandmasters, obviously very smart, and they wake up every day and they play chess every day, all day. And they're the best in the world, right? So what that means is that there's not really many things new in chess to these grandmasters. In fact, some coaches spend a whole year to teach their players one new thing. And the fact that we were able to influence the way that they play this much is actually pretty remarkable. Some of the qualitative comments that we got were clever, very interesting, not natural. This was one of my favorite. And it's complicated, not easy to understand, but very nice idea that's hard to spot. I want to add this slide. I read this article where Gukash won this, the youngest player ever to challenge the world chess champion this winter. And I saw his interview that says, my mental state has achieved something, was something that I hadn't really expected. And he added that I think I really improved in the last 1 year and in the last few months. And I was like, wait a second, that's when we worked together. And I looked back and I saw, oh yeah, that's, you know, chess players do this every day. He trains so much, and he's young, very passionate player. So I don't think we should take it to credit, but I hope that it was somewhat helpful. And I just remember Gukash being, we chatted on his, I believe, 16th birthday or 17th birthday. Like he's very young, and he was just most enthusiastic about working with us. He was like, yeah, I want to learn what AlphaZero thinks about chess and how it plays. And you know, that resulted in this great achievement for him. So congratulations to Gukash. So here's my one of my favorite part. Okay, in the audience, who plays chess? All right, who has elo rating more than 1800? Oh, all right. Yeah, we have some. All right. Okay. So these are for you guys. You're much better in chess than I am. So please, if you have questions, ask Lisa. But I'll show you. These are for you guys. So here's one of the examples that we learned, superhuman concept that we both, the Vlad and Lisa, and thought that is exceptionally beautiful. So here's the opening phase in chess. So in chess, there are some rules to guide us how to play. Some rules and openings that to control the center, develop pieces as soon as possible, and bring the king to safety. And the Grandmaster's choice does the first two, and AlphaZero makes the unusual move to also do the third. So for those who play chess, what if you have idea what move you would make next? You don't have to. B4? Knight takes B4. Okay. Okay. Anything else? Okay, yes. So Grandmaster made bishop e2 move, which does the two of the following. It does the control the center, develop pieces as soon as possible, and AlphaZero does something that does all three. This is what AlphaZero does. It reaches bg5. I'll give you a moment to appreciate and think about why it made that move. There are lots of examples in the paper if you're interested also. Because I find understanding this quite difficult on the fly. And here's how it does it. Boom. The queen is gone. I'll show you again. Bye-bye, queen. So what happened here is that AlphaZero decided to sacrifice queen. That's crazy. It's the most valuable piece in the game for long-term strategy game. So in chess, each place has a value. A queen is 9, bishop and knight together is 6. So AlphaZero traded 9 for 6. And the only reason, which humans don't usually do, and the only reason that humans may do this is for tactical reasons. There's a direct gain, like make the opponent. But AlphaZero does it for strategic reasons, to dominate in long term and provoke weakness in black. Grandmaster who trained on this concept increased performance by 50%. So if you're interested, there's a long appendix that we added in the paper with lots of other concepts that we heard from chess players that many of them are very interesting. There's some other interesting differences between what AlphaZero learned and what human does. AlphaZero doesn't abide by typical rules. So in human games, because humans can't really calculate everything, there are principles like you try to develop pieces as soon as possible and you only touch each piece once at the opening at least. AlphaZero doesn't care. AlphaZero touches pieces everywhere. They would develop a plan on the left and then move it to the right plan, whatever. So to conclude, communication between humans and machines is what we talked about today, and I argued that better way to do interpretability is to teach humans new concepts so that we can expand what we know and understand and communicate these machines better. And by doing so, by expanding what we know, I believe that we will also become capable of creating machines that could better communicate with us and works for us. Now, with the generative AI becoming more prevalent than ever before, there will be many, many more products. It's already impacting how teachers grade the homeworks, because students may use ChatGPT, Gemini to edit their essays. And more of these changes will come. We are in a position to make a decision. What kind of a relationship we're going to have? What kind of machines we're going to create? And what kind of a future do we and our children should live in? And I cannot emphasize enough how important role that you, experts in humans, will play in this decision. Humans are the most complex thing that humanity studied for the longest time. And the very object that requires and capable of expanding are humans. And you have power to bring the better future for ourselves and for our children. Thank you.
Hi, thank you for such an interesting talk. So I was curious, I really like how you have focused this talk on sort of expanding the H within this diagram, expanding our human knowledge. But I'm curious how you think about things that potentially are in the machine's representational space. I'm curious about things that you might think about in the machine's representational space that we might not actually want to be there. So basically, instead of expanding this H, maybe are there cases when we should be reducing this M? So
reduce M as well as maybe extend H. That's a That's a good point. Yeah, I guess expanding age kind of necessarily may also entail shrinking M, because as we discover some values and behaviors that we just absolutely can't accept, then we will shave that off. Yes, and expanding what we know will help us to build machines that can better do that. Yes, great question.
Hi, thank you for the amazing talk. I found this to be completely fascinating. I'm curious of what you think about this approach to sort of bridging the gap between human and machine understanding in the context of the rapid rise that we've seen in maybe the area of M, as it were, right? We've seen the space of machine knowledge really expand in the past couple of years and decades. And so as we examine a future which might have exponential rises in the area of M, I'm curious if you think this type of teach the humans how to interpret approach is going to scale with that exponential rise, and if you think that humans are going to be able to keep up with this approach as the capabilities of machines continue to take off, if you will.
Oh, that's a great question. So how do we keep up? M is going to grow exponentially and too fast. How are we going to keep up? I think humans have amazing generalization ability. Even babies have amazing, very rapid generalization ability. My daughter is 1 year old, and with 2 examples, she knows exactly what this means. This is milk. That's a very important thing. And that ability to generalize, ability to abstract out and make an abstract connection and reasoning at that level is going to hopefully give us a huge leverage over machines who may need a lot more hand-holding and examples. And it's more than that, actually. We have control. We make these machines, right? We have control over how far and how fast and what kind of knowledge we want to inject to these machines. So we have to actively think about our role in, okay, are they going too fast, too unexplored territory? Maybe we should think again. Maybe we should focus on, okay, we have to thoughtfully plan out what kind of knowledge this machine may acquire and think about that before making that, perhaps. So it goes hand in hand.
Thank you.
Good question.
Really amazing talk. And but I have just one curious question. So it's famous that like even human experts cannot teach other people. It's like if you want to learn soccer, like you don't want Messi to teach you, right? He's going to, okay, just do this. Like you're able to do that, and then I can't just do that. Like so, it's like a lot of cases, like soccer or even painter, like even a chef cannot actually teach you how to cut the potato into 1 millimeter, right? Like they are able to do that. So even human experts have this difficulty to transferring this expertise of knowledge into other humans. So like in the example of the chess, most of the experts have like 10 years of like training or learning. Like they're already on that level. And then so I just curious, like, so, and then you have the AlphaZero have this like some kind of a special case, and then you transfer that to human, and then they show really well. How much is that? It's just a small sample size there, or it's just we plateau on chess already? It's already there, but like, what about other skills or expertise?
Yes,
Yeah.
yes, that's a great question. So even experts can't teach humans, and how do we scale this up? Like other than chess, medical science, whatever. So I have this dream that we're sort of working on. And it's also part of my iClear keynote in 2022. If you're interested, it's a half-an-hour talk. I talk about this a little bit more. I think we need to develop a protocol or language, if you will, to support this communication from ground up. So what do I mean? Math is a language. We made that up, right? We have 3 apples. I sell 1 to Sam. How many apples do I have left? That necessity, that utility gave rise to development of this complicated language. And that language now enables us to comprehend, communicate, advance lots of complicated things. In fact, it's so important that we learn it from elementary school, or actually preschool, where my son goes to. So I believe that there has to be some framework to fundamentally transfer this sort of knowledge that we would have to expand as young as when we are babies. And I want to develop that sort of language. When I call it language, it drives linguists crazy. So I'm sorry if you're linguists in the audience, but it's a protocol or language, and that's how we're going to scale up this. And we may not be able to teach everything to everybody, but as long as the necessary knowledge is acquired by the experts who can perhaps guide and shaping the M, we'll be a lot better place than where we are now, is my view.
Hi. Thanks for the talk. I'm struggling to sort of resolve what I'm seeing as sort of a conflict between the first and second half of your talk. So that this chess result is fascinating, and as you said, you rely on, in some ways, the expertise of the grandmasters so that you can show them these examples, and they can learn the concept. And so I was thinking about that in relation to the visual feature visualization that you talked about, and there's the classic quote by Moravec in Moravec's Paradox, who says, you know, humans are all prodigious Olympians at like the basic tasks of vision. So if it takes the expertise of a grandmaster to learn from these examples, to learn a new concept in chess, why can't we take the expertise that we all have in vision to learn these visual features that these models are using? What am I missing there?
Oh, that's interesting. Oh, that's an interesting thought. Can we have a superhuman task in visual tasks and teach people? Yeah, I don't know what that could, you know, that would be interesting, another playground in addition to chess. I don't know what, clearly what superhuman performance that is convincing quantitatively what superhuman visual performance is, other than ImageNet classification, which the machines do better than humans. So that could be an interesting task. The reason that we chose chess is because we don't have to ask a lot of those questions. Because my goal with this work is that I believe that M-H has to be taught. And I just wasn't sure if it's possible. I just needed one example that this is possible. And I had to kind of shave off a lot of interestingness to make this happen. And even then, it took a couple of years. And now we have this evidence, we can start to think, okay, well, now it is at least possible in this one single cute toy domain. What else can we do? Thank you.